When you generate an image using AI, it needs around 3000 watts of power just to create that single image within seconds. Also, ChatGPT consumes an estimated 40 million kilowatt hour each day, which is enough energy to charge 8 million phones or run the Empire State Building for 540 days. Meanwhile, a single banana has enough energy to fuel your brain for the next 5 hours because your brain only uses 20 watts of power. But what makes your brain so efficient? If you look at the networks used in machine learning systems, they are densely connected. Every neuron in one layer connects to every neuron in the next, even if many of those connections are useless. And let me give an example of what I mean by useless. To calculate the value of this unit in the second last layer, we usually multiply different weights with all the units from the previous layer. But even if a bunch of those values in the earlier layer are 0, we still end up doing the multiplication. And if a weight itself is 0, that gets multiplied too. And all of these multiplications consume a lot of energy inside a GPU. The GPU calculates these values of the second last layer by multiplying a weight matrix with the outputs from the previous layer. You can think of this weight matrix as a big table that tells the system how much each input should contribute to the next output. The GPU multiplies everything in parallel. It never checks whether a certain multiplication is actually useful or not. Now let's look at how the brain saves energy by doing only the computation it actually needs. The brain has a huge number of neurons connected to each other, and the point where they connect is called a synapse. A neuron receives input through the dendrites, and that signal travels down the axon, eventually being passed on to other neurons through the axon terminal. A signal inside a neuron looks like this. It's basically a series of spikes at different time points, and each spike is called an action potential. When these neuron spikes travel from one neuron to another, they pass through the synapse, which act like weights, similar to those in machine learning systems, and produce a transformed neuron spike signal. This signal then continues to travel to the other neurons connected to it. Consider this network of biological neurons. When a spike input is given, they produce a transformed spike output. But if only one neuron receives a spike, only the neurons connected to it gets activated and start firing spikes. The rest remain completely silent and consumes no energy. In machine learning systems, each output node is connected to every input from the previous layer through weights. In the brain, however, a neuron can choose which other neurons it wants to connect with, forming only meaningful connections. So the main differences between the brain and the AI hardware are neurons in the brain only fire when needed and connect to only selective neurons, while an AI hardware runs the entire network for every input and the network is densely connected. Also, in AI hardware, memory and computation are separate. Every operation basically follows this loop. First, fetch an instruction from a specific memory address. For example, it can be adding two numbers, then move the data across wires, let the GPU perform the computation, which is addition in this case, and finally send the result back to the memory. This process then just keeps going. This is called the von Neumann architecture. The brain, however, works differently. When a neuron spike comes in, it's transformed by the synapse, which stores memory and does the computation at the same time. So the brain doesn't need to fetch data from somewhere else to process it. Now you might wonder, what's the big deal with fetching memory from somewhere else and then doing the computation? The problem is that moving data across a chip uses 10 to 100 times more energy than the computation itself. In other words, this transfer of data is causing more energy loss than the computation. Now, inside a GPU, there is a global clock that makes everything happen in a strict order. This clock ticks billions of times per second, and every operation, like addition or subtraction, has to line up with these ticks. This creates perfect synchronization in the GPU. The brain, on the other hand, doesn't have a global clock. Neurons respond only when there is a stimulus. In simple terms, the brain is event driven. For example, if you close your eyes, your primary visual cortex becomes less active and uses very little energy. This makes the brain an asynchronous system. But in the case of a GPU, even if you are not doing any computation or the processor is only waiting for data from memory to arrive so it can perform computation, the GPU's clock is still running, which again consumes a lot of energy. Now, the question is how can we achieve a brain like computing? Basically, we need to build a system with sparse connections, meaning each neuron connects only to specific neurons, not to all of them. On top of that, the system should be event driven. Also, the computation and memory should be close to each other. And this is where neuromorphic computing comes in. It basically aims to replicate the brain's computational abilities in a system that we can control and modify. Our brain uses a spiking neural network architecture. In this architecture, the input comes as a train of spikes, which is processed by layers of neurons, and the produced output is another train of spikes. If we look closely at a single neuron, it basically takes in a bunch of incoming spikes and turns them into one output spike train. This neuron follows what's called the leaky integrate and fire model. Here's how it works. Imagine two incoming spike trains. The neuron first integrates, basically adds up, the incoming spikes. Until the next spike comes, this accumulated value starts leaking. When the next spike arrives, it gets added on top of it and the value begins leaking again. Then another spike comes in, gets added on top, and the process continues. If this running total ever crosses a certain threshold, the neuron fires and produces a single output spike. After firing, the integrated value resets and the whole cycle starts again. But how can we implement this architecture in an electronic circuit? If you are thinking that I will basically connect all these neurons using wires and replace this neuron with a microprocessor to replicate the behavior of neurons in the brain, and that's it. So basically in this case, the microprocessor would act like a neuron in our brain. Now, if you look at the brain, it has around 86 billion neurons. This is not a big problem for us because we already have processors on a similar scale. For example, the Apple M4 chip has 28 billion transistors, and modeling a single neuron only needs about 20 transistors. The real problem with that idea is the number of connections each neuron in our brain makes with other neurons, which is close to 10,000. But if we try to do that in an electronic circuit, connecting each chip to 10,000 other chips, our hardware would reach its limit. We simply cannot create wiring at that scale because the brain is 3D while our silicon chips works in 2D. One solution to this problem is using virtual connections. But what exactly is a virtual connection? Let me give you a comparison that might help. In the brain, the time between two spike pulses is about 10 milliseconds, while in a CPU, it's only 1 nanosecond. So clearly, electronic systems can work much faster than a neuron. Now, can you think of a way to get rid of all those wires and still transfer spikes efficiently from the input side to the output side? Well, it's actually possible, just like a USB port, which only has 4 wires, but still it can transfer megabits of data in seconds. The trick is that spike signals arrive very slowly, but we can transfer the data extremely fast. Let me show you how this will work. If we put a router on the input side and assign a code to each input neuron, we only need 3 wires. When say the fifth neuron fires a spike, the router detects it and put its code onto the middle data line. On the output side, there is another router that knows which output neurons are connected to that fifth neuron. This allows the output neurons to selectively respond to only the appropriate input neurons. For example, if the fifth neuron is connected only to the first and the third output neurons, it will send a spike only to these two neurons. So basically you have replaced the physically connected wires with two routers that use extra memory to store information about these connections. This way, you need very few wires and solving the problem of having too many connections. Now let's see how IBM's TrueNorth chip achieves a power-efficient neuromorphic design using these ideas. A basic unit of this chip contains 256 neurons, and all of these neurons are connected to a router. This unit communicates with other units through the router. Using this setup, a neuron 3 at router 1 can get connected to neuron 255 of router 4 or similarly to other neurons. Now let's look at how these neurons make connections. You can represent inputs from different routers using red dots to indicate a connection. For example, input from neuron 234 in router 5 can connect to neurons 234 and 256, and other neurons can also receive input from different routers in a similar way. In a TrueNorth chip, a neuron can potentially connect to any other neuron, but it can receive input from a maximum of 256 neurons, which means that the total number of red dots for a single neuron is limited to 256. In the TrueNorth chip, each router has both a transmitter and a receiver. The receiver collects spike pulses from neurons in the other routers and sends them to a scheduler, which organizes all these inputs into a queue. Then a token controller, which has access to memory, delivers the spike to the corresponding neurons using its connected memory block. For example, if neuron 234 in router 5 is connected to neurons 234 and 256, it will send spike inputs to only those neurons. The same process happens for all other neurons. Now you can see that neuron 3 can receive input from many other neurons without having a direct physical connection to them. When these neurons fire in response to the inputs they received, the signal goes to the transmitter of the router, which sends it across the network to the receivers of the other routers. In this way, a neuron in this chip can be connected to any other neuron. Now you can see that we have created a sparse neural network where each neuron connects only to the neurons it needs to and responds only when a spike is received. Essentially, event driven processing. It also doesn't have a global clock, which means it doesn't need to wait for other processes to finish. And the most important part, memory and computation are close to each other. A TrueNorth chip has a grid of 64 x 64 neurosynaptic cores, which are the basic units of this chip. That gives a total of 4096 cores. Since each core has 256 neurons, the entire chip contains about 1 million neurons. Also, each neuron can receive input from a maximum of 256 neurons. So the total number of synapses is 256 million. This is still tiny compared to the 86 billion neurons in the human brain. But the impressive part is that the chip consumes only 65 milliwatt of power for a typical computer vision application, where a GPU would roughly use 20 to 30 watts.